Right. Hello, everyone. My name is Tuanang, and I'm currently a PhD student working with Frank, and today I'll be talking about inference compilation, which hopefully will become clear what it is as we go through the slides. So these slides are mostly borrowed from Frank. And just to introduce the problem, I would like to quote Andreas Sturmüller. Bayesian inference is computationally expensive. Even approximate sampling-based algorithms tend to take many iterations before they produce reasonable answers. In contrast, human recognition of words, objects, and scenes is extremely rapid, often taking only a few hundred milliseconds, only enough time for a single pass from perceptual evidence to deeper interpretation. Yet human perception and cognition are often well described by probabilistic inference in complex models. How can we reconcile the speed of recognition with the expense of coherent probabilistic inference? How can we build systems for applications like robotics and medical diagnosis that exhibit similarly rapid performance at challenging inference tasks? So in summary, we would like to perform asymptotically correct Bayesian inference, but we would like to perform it much faster than we currently can. There's evidence in the deep learning neural network that we can recognize images very fast, recognize images of dogs and cats very fast, but this doesn't translate to tasks in which we want to do proper Bayesian inference. So people have been tackling this problem for a very long time, starting with Peter Dayan and colleagues who worked on a framework called the Helmholtz Machine, in which both the forward kind of probabilistic program and the inference program was both, they were both neural networks, multi-layer perceptrons. And they come up with a method to train this neural network end-to-end so that they obtain the recognition network, which they, during inference, use for very fast repeated inference. More recently, there has been a reincarnation of the Helmholtz machine in the form of the variational autoencoder, which is really the same thing, but with a few new tricks which kind of make it work much better. And here again we have the decoder, which is in our language the probabilistic program, and we have the encoder, which is the program that helps us do very fast repeated inference. In this case, there are also either deep neural networks or multi-layer perceptrons. And so with new advances such as a lot more compute and the reparameterization trick, we have been able to train much larger models than in the case of the Helmholtz machine. However, there is one kind of drawback of this method, that is the latent variables, in this case the x there, is just a vector of real values instead of arbitrary latent variables in our probabilistic program. So after the resurgence of Helmholtz machine in the form of VAEs, people have kind of extended the idea of the VAEs, variational autoencoders, to be more structured. So in this case, Tejas Kulkarni in the MIT lab, they have come up with a framework in which they can do training in a variational inference, a variational autoencoder sense, in which the latent space is just not just a vector of real values, but they do it for a perceptual task where the observations are images and the latents are, for example, all the latent values that kind of generated the image, such as pose, light, or shape, or and so on. And what we would like to do, what I'll talk about later, is how this decoder can actually be a higher order probabilistic program in the sense that Frank introduced this morning. And I'll use a lot of the techniques that Gunesh has introduced from the deep learning literature. So inference compilation, what we would like to do. So we would like to denote a model and an inference problem as a probabilistic program in the sense that Frank has introduced in the morning. And we would then like to just hit compile for hours or days, depending on compute. And then afterwards, we get a compilation artifact. And this is supposed to be some sort of controller which helps us perform much faster inference when we get a new data. So the key point here is we want to perform repeated inference. We get a new test data, and we would like to perform very fast inference on this test data. We get a new data. We wouldn't like to run our MCMC algorithm again. We would like to perform fast inference. But as a trade-off, we spend some time up front to compile to get this neural network artifact. So I've already alluded to this. This compilation process is actually not compilation of programs in the traditional sense. It's trying to train a neural network so that we can get some compilation artifact that helps inference. So here we would write a probabilistic program, say in Anglican, and compilation is just a procedure which takes in training data from the prior of the probabilistic program, and then the output of this compilation process is a neural network architecture specific to the program and a set of trained weights. And this we call the compilation artifact. During test time, when we get an observation, in this case this y, we use the probabilistic program in conjunction with the compilation artifact to obtain asymptotically, this is the important point, we get asymptotically correct approximation of the posterior. This is opposed to deep learning, which just does one-shot classification, and we are not really sure what it means, under which model is it doing inference. Here we know exactly this is the inference under the model that we have specified as a probabilistic program.
What does SIS stand for?
Oh, it's, sorry, it's sequential importance sampling. It's a form of importance sampling algorithm, basically importance sampling. I'll talk about it in more detail. So this is just an overview. I'll go into each of the parts in more detail during the talk.
What are you training?
So there is a neural network that we train. It's a family of neural, sorry?
You have a data set. From that data, what are you training?
So we don't have a data set. This is completely unsupervised learning. The data is drawn from, we will derive a loss function that kind of enforces this.
Like if the training data is simulated from the problem.
That's right, yeah.
And then what are you, like?
So I'll go into the.
Some sort of a classification rule, or like, what is this neural net here?
We'll go into more detail later. It's not classification. It's trying to work on any generic probabilistic program that we want to write. So classification will only cut it for very few specific probabilistic programs. Any question? Any other questions? Yeah.
Do I get it right? The neural network is kind of a function approximator for your probabilistic program?
No. Oh well, yes. In the sense that Frank said, the running of the probabilistic program is backward. So yeah, it's kind of like an approximation of that backward computation. And then we refine it using our inference algorithm.
Like putting in a frame, I suppose it will be an approximation to the likelihood function at the level.
No, so we don't use the neural network to approximate the likelihood function. The neural network will get as inputs the observation, and then we'll try to approximate the posterior computation using our neural network. And then we refine it using the inference algorithm. Any other questions? All right. Yeah, so this is the picture I would like you to have in mind as we go through the talks. We have a probabilistic program, we train it for a while, then we get a compilation artifact, which is a neural net, and then we use it for performing very fast and, most importantly, repeated inference.
Things like what is the key here?
Oh, I'll go into more detail.
So
Yeah.
don't care the details. Okay.
Yeah, it's just, yeah. So this has a lot of connections with how people in the deep learning community have been doing things. For example, they have been trying to use synthetic data for text localization in the wild, or trying to break Captchas. But here people have actually broken Captcha because these are researchers from Google, and they had access to the true Captcha generation process. Okay, so let's be more specific. Let's consider now a graphical model. In particular, a graphical model which has finite number of latent variables and finite number of observed variables. So I denote latent variables as x. These are the variables that we would like to perform inference on. And the observations y, this is the things that we condition on. So the joint distribution is a product of all the latent variables given its parents times the product of observations given their parents. So here the goal is to efficiently compute, or at least the approximation of, the posterior, P of x given y, some expectation of a test function under the posterior, and to evaluate the marginal likelihood. This is important for model selection, among other things. So here's the Q that was in the image, and this the slide before, and this is an importance sampling algorithm. So is everyone familiar with importance sampling? Who is familiar with importance sampling? All right, so I'll go through it just so everybody is on the same page. So in importance sampling, we have capital K, which we call particles. We draw for each particle, we draw a sample from the proposal distribution. This Q is called the proposal distribution. We propose K samples for the latents, and then we weight each of these samples. We assign a weight to each of these samples, which is just the joint distribution divided by the density of the proposal evaluated at that sample proposed value. So this term will be easy to evaluate because that's the joint. Well, not really in the ABC sense, but let's ignore that for a while. But and then this Q, this is the proposal density which we have designed, so we should know how to evaluate it. After we kind of propose this K values and we obtain weights, we can normalize them, and using this set of particles, which is really just sampled values and weights, we can approximate the three required quantities. For example, the posterior can be approximated as a weighted sum of delta masses centered around the proposed values. The expectation under the posterior of the test function can be approximated as the weighted sum of the functions evaluated at the proposed value, and the marginal likelihood can be estimated using the sum of the unnormalized weights. So the important thing here is that these estimators are all asymptotically correct. But as you might have guessed, the performance of importance sampling is highly dependent on the quality of the proposal. We would like this proposal intuitively to be somewhere close to the area of interest. So what we will do is that we will adapt this proposal. So one notion of a good proposal is to make the proposal as close as possible to the posterior P of x given y. So we have introduced this new parameter lambda to the proposal distribution, and we would like to make this family of proposals induced by this lambda parameter to be as close as possible to the posterior distribution P of x given y. So one notion is to make it close in the KL divergence sense. So is everyone familiar with KL divergence? Right, so as you all know, KL divergence is not symmetric, and if you optimize the KL divergence from P to Q with respect to lambda, it's, you get something different than when you optimize KL divergence from Q to P with respect to lambda. So imagine now your P distribution is a mixture of Gaussians with two distinct modes here. And the family of Q distributions is, the Q distribution is a family of Gaussians where lambda is the mean and the standard deviation of this Gaussian. So if you optimize this KL divergence from P to Q, you obtain the behavior like this. The Q will kind of cover both modes. It will spread its mass among the two modes of the P distribution. However, if you optimize this KL divergence, i.e. from Q to P, you obtain this kind of behavior. So this is very common in variational inference if you're familiar with variational inference. It will kind of spread its mass. It will concentrate on one of the modes of the P distribution. So in this case, in our case, we'll focus on this version where the distribution of Q concentrates on as many modes as possible of the target distribution. Okay, so this is explored in a technical report by Tom Minka, and it's very interesting.
I'm a bit confused here. In the figure, you say you are actually minimizing alpha divergence.
Yes, so these two KL divergences, they correspond to alpha divergences at the extreme values of alphas. So here, alpha is minus infinity corresponds to KL divergence from.
That I get, but okay, so what is the difference between your first KL divergence and the second one? Okay, so
first is P and then Q and P. So the KL divergence is not symmetric.
Yeah, no, that I know, but like, so which one you are using then?
We will be using this one, which corresponds to this case. The proposed.
You're not using alpha divergences because it's in the figure. So
Yeah, this figure is just to illustrate the differences between like the two extremes of this distribution measure. Yeah, so we'll concentrate on this KL divergence, which makes the proposal distribution spread around as many modes as possible. And that corresponds to alpha equals infinity. Okay, so this is probably the core idea, core slide that about inference compilation. So here we try to optimize lambda, but we would like to do so. We would like to optimize with. We would like to have this lambda good for a variety of observations y. So what we do is we say lambda is not just a value we optimize. Lambda is an output of a function, a parametric function. In this case, it will be a neural network, as we see in the next slides. It will be the output of a neural network which takes in observations y and is itself parameterized by another set of parameters, the neural network weights. So the neural network here is phi, and the parameters of the neural network is this eta here. And this. That's right, that's the weights of the neural network, and it itself takes y. So this neural network preferably will just take the y and output a very good proposal parameter. So for that, we kind of need to change our objective function a bit. So we will not only optimize the KL from P to Q, we will optimize its expected value under the distribution of the observations that we might see under this model.
Y was your observed data, right?
Yeah, that's right. X latents, Y observed. So we'll now optimize not with respect to lambda, we optimize with respect to eta, the parameters of the function that outputs lambda. So let's go through this equation. In the first.
Do you have any assumption on the functional form of Q?
As you will see, we'll have some assumption, but for now, let's just say that we just deal in very generic case, very abstract case. We will have to kind of say what is the family of Qs that we have. So this is our objective function. In the first step, I just rewritten this expectation of the KL divergence in the integral form. In the second step, I write the definition of the KL divergence in the integral form. It's the KL from P to Q is the integral of P log P divided by Q. In the third step, we kind of combine P of y and P of x given y, and we obtain P of x and y, which is the joint distribution. And we know the log is just log of P divided by Q is just log of P minus log of Q. And then in the last step, we notice that some of the terms in the integral are not dependent on eta. And so we lump them into a constant with respect to eta. And we are left with just expectation. Yeah, so we are left with an expectation of something under the joint distribution. And that something is minus log of the density of the proposal distribution, where the parameter is the output of the neural network. And this is just an objective function on this eta. So this is in a very nice form in the sense that it's an expectation under a distribution from which we can sample from. If we have a probabilistic program, we can sample from its joint distribution. We just run the program forward, not in Frank's sense, in your sense. We just run it forward and get samples from the latent and observed values. And then we use those to perform stochastic gradient descent, i.e. we just use those and plug it in to log of qx given lambda, and then we get derivatives from just an AD package. In this particular case, we use PyTorch. And we just optimize for days, hours to obtain a compilation artifact. So let's have an example. Let's have a concrete example. So here we would like to do polynomial regression, Bayesian polynomial regression. So we will have a prior over the weights. In this case, the weights are distributed according to a Laplace distribution with mean 0 and the scale which decreases as the order of the polynomial increases. And the observation is distributed according to a student t distribution with the mean being the output of the polynomial and some fixed scaling. And so here's the graphical model. We have some weights, we have some inputs and the outputs of the polynomial regression. And we would like to perform inference to see what is the posterior distribution on this weight. So since this is a finite graphical model, there are algorithms that allow us to invert the model in the sense that the observed variables now don't have any ancestors that are unobserved. And then looking at the inverted model, we can hand design the form of the neural network. So here is one instantiation where we hand design how the the form of the neural network looks like. In this particular case, the neural network will just take the inputs and the outputs, and the output of the neural network is proposal parameters for each of the weights. And in this case, it's we say the family of distributions is a 3-component mixture of Gaussians for each of the weights. So the output of the neural network will be the means and the standard deviations of this mixture of Gaussian. And some details, we will use a 2-layer multi-layer perceptron as a neural network, and the hidden state will have 200 units. Yeah.
Give us then one more time, why is this inversion necessary?
So this inversion necessary, it's not really necessary, as we will see later, but this inversion helps us to kind of come closer to the kind of dependency form of the posterior distribution. This helps us to have the dependency be closer to the dependency structure of the posterior distribution, and so helps the neural network learn faster. So here are some results of after we optimized this neural network in the previous slide. In this case, it's just a few minutes. We optimize it, and here we perform inference on 3 different data sets. In different rows, you can see different data sets. The black dots are the inputs and outputs of the polynomial regression task, and we see different cases of this input-outputs. So on the very left, we see inference with Metropolis Hastings, which is an approximate algorithm, since in this model is non-discrete, non-linear, non-Gaussian, so we don't have exact inference algorithm. But running Metropolis Hastings for a lot of iterations is good enough to tell us, okay, this is a very good approximation of the posterior. In the second column, we see the prior distribution of the polynomials, of actually the weights, but we draw the weights as the polynomials. In the third column, we have the Q distribution. After we learn the neural network, now we kind of plug in the observation into the neural network, and that outputs this distribution of the proposals. We then use this proposal inside an important sampling scheme to perform inference, and we obtain this. So we can do this for different data sets at test time. So just to iterate, we train the neural net very long time, and at the inference time, we get test data, and bam, we run the neural network just once forward, and we get this. Then we just use it as important sampling proposal. And here, as you can see, the proposal is very close to the posterior already. So in the important sampler, we'll not have to do a lot of work. Any questions about this?
Can I see all this as you use a neural network to build a clever proposal in an important system?
That's right. That's right. Yes. That's right. Ideally. That's how we design our loss function. Ideally, for a y, it'll just, bam, here's your posterior. Okay, so that was for finite graphical models, and we now want to do it in the case of higher order probabilistic programs, as Frank has talked about in the morning. How can we do this? So the main difference of higher order probabilistic programs to finite graphical models is that the graph is not finite. We don't have finite number of latent variables. And so we'll have there's a concept called execution trace, and it's very simple. Execution trace of a probabilistic program is just a sequence of samples. And now what is a sample? A sample is just a tuple of a sample value. Like when you run the program, you get a sample value at each sample statement. Each sample statement will have its address, and it will have its instance, which kind of denotes how many times we have seen this sample before during the running of the probabilistic program. And importantly, we have the trace length. And this can be different from program to program. In programs where we have for loops, where the end condition is itself a random variable, can loop for variable number of times. And so we can't kind of use the inversion algorithm for graphical models that I showed in the previous slide in this case. So the joint probability density of a higher order probabilistic program is very similar to that of a finite graphical model. It's just the trace length is different. It's still a product of these conditional priors of sampled values given the samples before, times the product of the likelihood terms of the observations given all the samples before. So here is the family of neural networks that we have designed to work for inference compilation in higher order probabilistic programming. And it's just so we will have a non-program specific stacked LSTM core. Is everyone familiar with LSTM, by the way? Who is familiar with LSTMs? Who is not? Oh, okay, great. Okay, I'll talk about LSTMs for a bit. But just imagine some neural network architecture, and it will compose, the core will be this LSTM construct, which allows us to run the neural network for arbitrary length input sequences and output sequences. It will contain a lot of proposal kind of neural network modules, observation and sample embedding specified by the program. So maybe I should do a short thing on LSTM. So an LSTM was incidentally invented in Lugano by Jürgen Schmidhuber. And here, in my mind, I just see it as a function with deterministic function with some parameters. And here is the functional form. And at every time step, we have some initialization of this. This is called a cell. This is called a hidden variable. We have some initialization to 0, for example. And then for each time step t, this deterministic function just executes in the following way. It just calculates some matrix multiplication times plus some biases, runs it through a nonlinear function, and these weights, W, U, B here, these are the things to be learned, and we can run this in a sequence, basically. And we don't really need to worry about when we want to optimize the output of the LSTM with respect to some loss function. We don't really need to worry about how to do the derivatives, because before automatic differentiation, people have gone in and like unrolled these equations into different time steps and calculated what are the gradients of the loss function with respect to each of these weights. But here we just run this program forward, run this neural net forward, and using automatic differentiation, we automatically get the gradients of the loss function with respect to these weights of interest. So this allows us, this LSTM construct allows us to run for arbitrary length sequences. And is actually the neural network architecture behind some of the successes of machine translation, and as Gunesh says, speech recognition and all that. So here we see LSTMs running. This is the family of the proposal neural networks, and we see the LSTM being used here. It's at the core, and in compilation time, we just add new layers attached on the fly on first encounter with the address instance pair, and during inference, we just use this neural network to propose the values in the trace. So this is a bit unclear, but I will go through one particular example to illustrate the neural network, how the neural network runs. So let's consider this probabilistic program for generating captchas, written in a pseudo Python probabilistic programming language, and it goes as follows. We initialize letters to an empty sequence, and then we sample number of letters from some distribution, let's say uniform discrete from 3 to 10. So we say our CAPTCHA will have 3 to 10 letters uniformly at random. And we have a loop which loops over each of the letters and samples, appends to the letters sequence, a sample for that particular letter, uniformly, let's say, from an alphabet. And then we render, using some render, we render the CAPTCHA image, and we condition on the observed CAPTCHA. And when we return, this means that we want the posterior of the letters given this observed CAPTCHA. So in the exercises, we'll go through this more, and we'll actually use ABC distance to do this observation, conditioning operation. So in this program, there are 2 sample statements, and we'll assign, there will be assigned a sample address for each of the sample statements. Let's say this sample statement for number of letters is A1, and this second sample statement is A2. Any questions about the probabilistic program for generating CAPTCHAs? Okay. So now I'll go through like how to, now imagine that we have trained a neural network. How we train I'll talk about later, but let's say it's trained. And now how do we get a proposal? So in this case, you see the loop itself, the end condition of the loop is itself conditioned on something that is random, so the loop can execute for a variable number of times. So I'll now talk about how we get a proposal value. So this x that corresponds to a latent variable in this program. What do you think is the latent variable in this program? Or the x? Letters. That's right. We might be interested in number of letters, but yes, letters and number of letters. So I'll go and say how we could propose these quantities from a proposal distribution that is already learned. So first, we pass the observed CAPTCHA. This is, for example, a CAPTCHA that we want to condition on through an observation embedder. This is, in this case, will be a convolutional neural network, and we get an observation embedding. And we run the program forward until we hit the first sample statement. We evaluate using an interpreter for a probabilistic program. We run it forward until we hit the first sample statement. When we hit the first sample statement, we would like to ask the neural network, give me the proposal value, give me the Q for this sample statement. So what we do is we take the observation embedding, we concatenate it with the previous sample embedding. In this case, it's 0 because this is the first sample we encounter. Since this sample statement has an address A1, we have a unique mapping from addresses to one-hot vectors. An instance is 1 because this is the first time we encounter this sample statement. And the type, which is uniform discrete, also has a unique mapping to a one-hot vector. We concatenate all of these things, and we input it to the LSTM. And remember, LSTM is just a deterministic function that runs forward, and you can evaluate it at every time step, and it will give you an output. So the output of the LSTM is passed, again, through a proposal layer, which is specific to an address instance pair, and it will output the proposal parameters that are hopefully very close to the proposal is hopefully very close to the posterior. So in this case, say it's 6. Like looking at this, you see it's 6 letters. So hopefully the proposal is a distribution that concentrates on 6. And then we obtain a sample for this proposal. And then we use this in the probabilistic programming interpreter. And then now after that, we use the sample and we continue executing the probabilistic program. And we hit now the second sample statement. What happens is that we take the sample from the proposal, and we again take the observation embedding. We take the sample from the proposal, we pass it through some sample embedding. We look at the address of the sample statement. It's A2. That has a unique mapping to the its own one-hot vector. It's different to the one-hot vector of A1. The instance counter is 1 because this is the first time we encounter a sample from this sample statement. And the type is uniform. So we do this again, and the proposal here hopefully will return a proposal distribution. So now the first letter is a bit unclear what it is, so hopefully the proposal will be like, it's Q, A, or O with this kind of probabilities. We take a sample, and we then continue, and this goes on and on. Here we can see the instance counter at the second iteration of the for loop becomes 2, so this one-hot vector becomes something different than in the first iteration. And we just go on and on until we hit the very last sample statement. And the end is kind of denoted, we know it's the end because the execution of the probabilistic program has stopped. So that is like some signal to the LSTM. Okay, now we are done. So in this example that I've showed, we have been able to propose this sequence as a proposal for the latent values from this proposal distribution. And this, note again that can have different length depending on number of letters. Wait, sorry, is there any question about the running of the neural network during inference?
Probabilistic programs that have variable length of instructions. In this case, we know that the number of instructions will always be the same, the number of samples. But we could have a program that has variable number of.
Yeah, good question. So in this case,
Well, actually, we're drawing it from non-letters, so this already.
Yeah, so this already has, like, in another execution. So this was one particular sample. This happened to have 6 letters. But let's say you run this proposal once more from the neural network. It could have, if the number of letters was unclear, for example, the distribution here would not concentrate on 6, it could have proposed something else. And it could run, it could generate, it could propose a trace which has different length. It could be something else. And this is just a simple example. This Captcha model is really a simple example. But this is trying to work on a generic family of the programs you can write in probabilistic programming languages. So then we just do the standard thing. We evaluate, and we get a posterior approximation of this, of the posterior given this Captcha, posterior over the letters. So here, for example, we can see it can be uncertain. The first letter is Q or A or O. And this is different to a deep learning approach, right? In deep learning approach, you must get, you get a bunch of input-output pairs, captchas and letters. And then during inference, you get kind of an output, but you are not really certain. The output doesn't really correspond to any sort of probability. It is an output of a softmax, but you can't really say, well, this is a posterior under the model, some model. Here, on the other hand, we say, oh, well, these probabilities correspond to our approximation of a posterior under the model that we have specified. So here we have a handle on kind of what model we are performing inference on. So I did this in a bit of a reverse order. So compilation, now it's very clear how you would do compilation. You would just generate training data from the prior, because see, the objective function was an expectation under the joint. So we just generate kind of training data from the probabilistic program by running it in your way. And this will fix the inputs and the outputs and the length of the LSTM for every trace. And then we just do backprobe. We just call backward. Done. Is everything clear?
So you don't need real training data, you generate training data?
That's right. So the way we derived our objective function is an expectation under the joint distribution. So to optimize that, we can just sample from there sample from the joint distribution and plug it into the thing in the expectation and evaluate its gradient to perform stochastic gradient descent.
Isn't this a little bit like cheating? Like if your model is wrongly specified, you're in bad trouble.
Yes, very good question. Yes, if the model is misspecified, we are in big trouble. But
You reinforce your errors.
that's right. So we will kind of, when we do inference, we will do correct inference under the model, but the model is wrong, so the inference will not make sense. So we would need to think a lot harder about what is the correct model for this task.
Right, so with the simulator, it assumes true.
Sorry?
The simulator model that you have is assumed the true model.
Assumed to be a true model, or we are responsible for making it the true model. But if we are in a situation where we have a true model, and there's a lot of cases like physics, engineering simulations, we have the true model, and we would like to perform repeated inference, i.e. we would like to have inference that, like for every new test data, we would like to do very fast inference, we can use this technique. But if the model is...
What about like you don't do it sequentially, you have like 1,000 simulations already prepared, and then like using all of them simultaneously, you can send the network, right?
That's right. That would work very well. We're actually working on parallelizing the training procedure, and maybe we'll need your help on how to do this properly.
But yeah.
And yeah, another point. Yeah, this is parallelizable, both during training and inference, because this is just embarrassingly parallelizable. Okay, so the implementation is in the probabilistic program you can write in Anglican. The neural network is implemented by us in PyTorch, and the communication between the two is done by something called 0MQ. And we will do an exercise for solving captchas during the exercise session. So here are some examples of this working on models that are not slightly more complicated than just models expressed by finite graphical models. For example, here we have an open universe Gaussian mixture model where the number of clusters is not fixed beforehand. Number of clusters is a sample itself. And for every kind of cluster, we generate its parameters, and for every data point, we generate the cluster label, and we observe. And we want to return the posterior over the parameters. Here we do some comparison with sequential Monte Carlo, and here we see kind of how inference, or like the proposal gets better, gets closer to the posterior as we do more training. So here we see kind of the...
People are there.
No, so we use a detector which kind of outputs the detections of these objects, and we would like to see how many kind of people are in this picture. So we use Gaussian mixture model to kind of count and localize.
So each people is a Gaussian.
Yeah, we assume that's our assumption. This is just a toy model that we did it on.
I'm trying to understand what's going to be.
So we get like some trained output, trained neural net from outside. We get the detector outputs, and then using the detector outputs, we would like to count how many people are here. So we do it in the context of an open universe Gaussian model, Gaussian mixture model. Here we have our Captcha, a bit more complicated than the one I showed you before. And we employed it. So this Captcha model is very similar, just we have sampled some additional things such as the kerning value and some noise parameters, the font, etc. And here we can see it working on actual real data. So we tweak the model so that it is a good model. And we kind of deploy this inference compilation task on actual data. So the first two rows correspond to data from, can anyone guess? Not really, okay. Facebook Captcha. And the two last rows is Wikipedia Captcha. So we did this on real data, and we can see actually where we can see actual uncertainties in in the posterior approximation that we get. So if we take the maximum a posteriori estimate of the posterior approximations, we see that we actually get state-of-the-art results. And here we see the effect of training on the quality of the proposal and the posterior. As we get more training, the map gets more, the posterior gets closer to the truth. So in this case, it was 10 million.
That's big.
That's big.
That's because if you were, like, most of the time, simulated models are like 7 minutes, 8 minutes, 1
Yes.
second.
So for this performance, it took us more than a week to get this performance. But then, if you give me a new Captcha, I can tell you, this is the posterior.
That's offline.
Okay, so that's the end of my talk, and I would like to summarize kind of what we have been talking about today. So in the morning, Frank has talked about probabilistic programming, and that is kind of a method to kind of have a unified model denotation and automatic inference. Gunesh has then talked about deep learning and automatic differentiation. This is a very powerful regressor, function approximator, but needs a lot of training, label training data. And now I've tried to kind of tie the two in, marry the two, and in this inference compilation framework, where I try to do fast repeated inference, and training data is actually generated from the probabilistic program. So thank you for your attention, and we'll do this exercise in the
Actually, we have time until 12:15 because the food is coming late. So if you want to slow, it's coming at 12? Yes, but you said it's coming at 12. So then we can stop here and go for work? Okay, so that's fine then. So if we have any questions for... Yeah, so we have 9 minutes for questions. We have a lot of time.
Any questions?
I'll ask some questions on models and questions. So what if you actually have XY pairs? A few. What do you do?
We just use it as part of our training data. So the Russian mafia comes to me and puts a gun to my head, but I say, okay, I have these 2 friends that can label some data. So I let them label a lot, and then I use them as part of my training data. Okay. So the question was, what if I have some training data, labeled training data? And the answer is we just reuse them, use them in the set of training data that we generate from the probabilistic program. But there are some more subtleties that we can talk about offline.
In your slide that during the compilation process, you fix the length of the LSTM. This is to say you have some general size LSTM that you can trim with dropout or something like that.
No. So the size of the LSTM is fixed per trace. I forgot to add that part here. So when you generate this training data, each kind of training trace, like a trace from a probabilistic program, will have different lengths. And what I've tried to say here is that every trace will have a fixed length. Although like the length will be different across traces, every trace itself will have a fixed trace. And that kind of fixes the LSTM. That's right.
Okay, so that relates to my previous question. So you basically train one LSTM, but how many times you loop depends on the individual trace.
That's right. Yes.
I'm coming
Yeah, so the question is, what is the family of proposals that we use? So the family of proposals that we use is kind of described by this neural network, really, and maybe you're asking what is the very last kind of, what is the actual distribution that we sample from? So in this particular implementation, we have a proposal distribution for every distribution. So we hand design like the form of the proposal for every kind of elementary sample statement that can occur in the probabilistic program. And there's only a finite number of those. So we go and we say, okay, for a Gaussian, we would like a Gaussian proposal, etc.
But in a sense, you're finally getting this deep neural net.
That's right. So,
That's the function. So
yeah.
your function will be of a type of LSTM or any of those things.
That's right. So most of the work will hopefully be done by the neural network, and at the end, it's just.
Learn a neural net.
Yes.
That's the family.
Yeah, that's the family. And the very end here, what is the actual form of the proposal? That's like specific for each elementary kind of sample distribution.
Any other questions? Okay, I think I have. Okay. No.
Could you generalize this model to sampling probabilistic programs?
Of course.
So you could make it into a system that does both, but it will be very computational heavy because you have to sample a program, then you would have to train a neural network to approximate that.
Yes.
But in principle, you could generate, it would be kind of a way to.
Yes. So in principle, your probabilistic program can actually be, the latent variables can actually be a text of another probabilistic program. And Frank has shown some slides on that in his talk. Like, if you write that model, yes, this will work. I mean, this will run. Whether it will work is another question.
Anybody? No. So I think I will just ask. It's quite an exciting work. What is the reference? Like, if I want to refer this work, is it already published or?
Yes. So.
If you can point to that. You can send me.
I can send you later, but.
That's fine. Is this the paper, this page and wood?
So that's the precursor. This page and wood is.
There's one for finite dimensional model, which is the ICML paper, and then there's one for higher order.
The GMM one.
That's ICML.
That's for finite graphical models.
Okay.
And we have worked on an extension which I didn't, for some reason, include the